Good. So let's start. In 4-1. So exponential functions. Our basic exponential function. Sometimes people call this a base exponential function. Is one that can be written as f of x is equal to a base to a power. Now we are going to have other exponential functions that involve more operations. But at some point, it's going to have a base to a power, where our variable is in the power. And this b is called the base of the exponential function. All right? We always force our base to be positive and not 1. And again, what makes an exponential function is that the variable, our input variable, is in the exponent, right? Is in the power. That's why we call it an exponential function, or variables in the power, or in the exponent. Now, why would we force our base to be greater than 0? Well, we force our base to be greater than 0 so that we can have real number inputs. Okay? If my base, let's just say, was -2, and I wanted to take -2 to a power like 5, that would be perfectly all right. Just -2 times -2 times -2. But if I try to take -2 to the power of 0.5, all of a sudden that's an uncomfortable scenario. In fact, 0.5 is the square root, right? So that would be the square root of -2, which would be a complex number or an imaginary number. And it gets even trickier if we wanted to take like -2 to the 0.1 power. Okay, well, that's a 10th root. What does that mean in terms of the negative in there? Or what if I want to take -2 to some irrational power? Like the square root of 3 power. That would be impossible to do, right? With negatives. So that's why we force our base to be greater than 0, so we don't have these issues. So we don't have complex numbers going around, and so we can figure out that. Now, some of the properties of our base exponential function. Well, the first one is that as long as we make our base greater than 0, we don't want our base to be 1, then it's continuous over the real numbers. So the domain of our exponential function, our basic exponential function, is going to be all real numbers. Also, there's no sharp corners. We'll see a graph, or a few graphs, I should say, in just a minute. And we'll see that there's no sharp corners on these exponential functions. It goes through the point 0, 1. Any number to the 0 power is equal to 1, other than 0 to the 0 power. That's what's called an indeterminate form. We have a horizontal asymptote of y equals 0. On one side of the exponential function, it's going to go off to infinity. On the other side, it's going to approach the asymptote. So one side approaches a y value of 0. The other side goes to infinity. And then lastly, it is a one-to-one function. So not only does it pass the vertical line test, which makes it a function, but remember back in unit 1, we said if you pass a horizontal line test, it's a one-to-one function. I'll draw 2 pictures. And you'll see why I draw 2 pictures in just a moment. But one of the pictures I'll draw with my horizontal asymptote on the left-hand side and going off to infinity on the right-hand side. The other, I'll draw in the reverse way. Goes off to infinity. Okay. On one side, on the left side this time. Whereas I got a horizontal asymptote approaching the horizontal asymptote on the right side. Okay. So it's gonna look like one of those two things. And here, let's just do f of x is equal to 3 to the x power. That's a base exponential function with base 3. So basic exponential function with base 3. Notice it goes through the point 0, 1, as all of our basic exponential functions do. It shoots off to infinity on the right side, goes towards 0 on the left. Okay? It turns out no matter what your base is, let's just say B, we'll add a slider. No matter what your base is, as long as your base is bigger than 1, it's going to have that basic shape. Now, when the base is 1, 1 to any power is just itself. So we get a flat horizontal line. That's why originally we did not want our base to be 1. Right? Remember we said we wanted our base to be positive and also not 1. A base of 1 is just a line. It's not very interesting. But anytime my base is bigger, like my base is 1.2, I get that basic shape. And as the base gets bigger and bigger and bigger, all that happens is it shoots up a lot faster. Okay. Base bigger than 1, we get that basic shape where on the right-hand side, it's shooting off to infinity, and on the left-hand side, it's approaching y equals 0. Now, where we have the other shape is when our base is below 1, but bigger than 0, all right? So something like 0.8. 0.8, on the left-hand side, we shoot off to infinity, and on the right-hand side, we approach y equals 0, the x-axis. And as your base changes, it just gets steeper and steeper. And by the way, if you let our base be negative, you see you can't graph most of those. So if you have a negative base, you'll see that there's no graph there. So 0.1, 0.3, 0.4. Now, this is not something, how do I say? So 3/2 is bigger than 1, right? So here's the graph of f of x equals 3/2 to the power x. If I look at another function, which is the reciprocal function, notice what happens. The reciprocal function, if I take the base and use the reciprocal rather than the base itself, all we've done is we've flipped over the y-axis. All right. Why is that? It's the flip over the y-axis there. Well, the reason that's the case is because negative exponents, that's what's on left-hand side here, right? Negative exponents are the same thing as doing a positive exponent on the reciprocal, right? So if you remember your exponent rules, negative exponents are me doing a positive exponent on the reciprocal. Okay. You don't have to write this down, but if I take a to the negative power, that's the same thing as 1 over a to whatever positive power. That's what I'm saying. That rule. Okay. That rule of exponents. So that's why it's flipped. So that is our basic exponential function. All of our basic exponential functions look like that. We're not always going to deal with our basic exponential functions. We will look at other exponential functions. Because exponential functions, just like all of our other functions, we can translate and shift and multiply it by a number to stretch and do all that kind of stuff. So we can do all kinds of different operations and make them more complex, but this is the starting block. Just like y equals x squared is the basic quadratic, right? It gives us the parabola. This is the basic exponential function, right? And it gives us that graph. Now, as far as calculations go, obviously you could spend a whole lot of time doing calculations of things where, I don't know, you take 4 to the 5.6 power. Let me just rewrite this. So let's do some calculations. Or 1/8 to the negative third power. Or 7 to the 1.6 power. Or even something like 3.2 to the square root of 5 power. Okay. These first three, we could probably do by utilizing some sort of a root and powers and rewrites to powers and things like that. That's what you can do when you have rational exponents. When you have irrational exponents, you can't really do that. So on all of these, rather than trying to rewrite these with rational exponents and things like that, roots and going through that process, we're just going to turn to our calculator and utilize our calculator. That makes sense. So four to the 5.6 power. Obviously, I'm gonna get some ugly decimal. But when we get our ugly decimal, we'll probably just round it to 2 decimal places. And say 2352.53. 1/8 to the negative third power. That's a nice whole number of 512. Seven to the 1.6 power. It's an ugly decimal, but if you round it to 2 decimal places, it's 22.50. That 49 rounds up to a 50. And then 3.2 to the square root of 5 power is about 13.48. Is that all right? Now that's just a straightforward plug it into our calculator. It shouldn't be very difficult to do. You can also do this with function notation. With function notation, we're going to say something like if I have a function that is 1.25 to the x power. Let's find the following things. What do you get when you plug in 4? What do you get when you plug in 8.7? What do you get when you plug in negative 3.1? You know, we can do stuff like that too. And just like the calculations, we're just gonna do this using our calculator. F of 4, we take 1.25 to the 4th power. And I get roughly 2.44. When I plug in 8.7, I get roughly 6.97. When I plug in negative 3.1, I get 0.50, rounded to 2 decimal places. Again, that should not be anything too crazy, I hope. Plug things in just like we would any other function, and then we're going to utilize our calculator. And that's especially important when I have exponents that are hard to deal with. Even the rational exponents are hard to deal with. You could trace through some things by hand with those rational exponents, but much better just throw it in your calculator and get an approximate answer. In almost all cases. Now, one thing that's going to come up a lot in exponential functions is this number e. I'm sure many of you have seen the number e before. It's on your calculator. E is this number that is linked to exponential functions. That's very common when we're dealing with exponential functions. And it is an irrational number that's approximately 2.71828. And then technically it goes on and on and on forever, but it's irrational. That work? It's on your calculator, and on most calculators, there's a straight E button and an E to the power. Because E is so linked to exponential functions, it already has like the power on it. And on the TI-84, it's second and then the LN button. So down on the left-hand side, right across from the 4, there's an LN button. If you hit second and then that button, you get E. Now, I will write this down. It might not make sense. E actually is this number, but it comes from the limit as n gets really big. Of 1 plus 1 over n to the n power. You know how we have the arrow notation? Well, that arrow notation translates into limit notation when you get to calculus. So if you get into Calc 1, you deal with a lot of limits. And that's where E is actually coming from. Basically, this number becomes like this number when n gets really big. Let me show you that on the calculator. I'm not going to go through this in great detail. Let me do this first. So first off, E to a power is this button. I know I said that, but there it is on the TI-84. If I take 1 plus 1 over a number, let's just say 8, and then take that to the 8th power, I get this 2.56 and some odd change. There we go, a little less bright. Now let's change that 8. Well, just for sake of ease, to an 80. I get 2.70 something or other. Now let's change that 80 to an 800. 2.71 something or other. So you can see we're getting close to 2.7 something or other, right? And then you just keep messing around. Now it doesn't always have to be 8s, obviously. You can do 99999. So 5 9s, 999. What's gonna happen? You're gonna get that. 7.1. And as you get bigger and bigger and bigger numbers for your n, just start counting. Any more 0. Yeah. I'm getting, as I get bigger and bigger and bigger numbers, I'm getting close to that 2.71828 number. That is E. Like E to the first, right? Getting closer and closer and closer to that. So that's what we mean. We mean as that n gets bigger and bigger and bigger, this value, whatever it happens to be, gets closer to the E. So that's the idea. That's what this number E is. That's where it comes from. Now, in terms of utilizing E, we can utilize E just like any other number. So if, let's say I have a function, we'll call it g of x equals e to the x power, we can find, for instance, what we get when we plug in 6, or what we get when we plug in, I'm thinking of 5.2, or what we get when we plug in a negative 1.8. And we can use it just like any other number. We turn to our calculator in each instance. E to the 6th power, I use second ln, and then just put a 6 in the exponent. Gives us about 403.43. E to the 5.2 power gives you 181.27. And again, I'm just getting this straight off my calculator. You guys okay with getting these things off your calculator, hopefully? And then E of negative 8.1. No, I'm sorry, negative 1.8, excuse me. Negative 1.8. It's equal to about 0.17. Okay. So that's our basic standard exponential function with different bases. Now, what are we going to do? Well, we're going to use exponential functions that arise from our basic exponential functions with standard basis. We're going to say, well, instead of just e to a power, let's put a coefficient out in front of here. And instead of maybe just to the x power, let's do something else in the exponent. All right? And we can do that not just with base e, we can do that with any base we want. And so we can use other exponential functions too. So we want to use other non-basic exponential functions like this. Let's say if I have a function which is 750 times 1.37 to the x power. All I've done is take a basic exponential function and stretch it by multiplying it times 750. Okay, so all that is just a stretch. And we could find, by the way, this one, because we're stretching it, this is not going to go through the 0.01 anymore. But it's going to have a lot of the similar properties to our basic exponential function. It's going to be defined over the real numbers and continuous over the real numbers. It's still going to be 1-to-1. It's still going to have the basic shape, but it's not going to go through 0-1 anymore because we stretched it along the y-axis in this case. All right. But we can still calculate just as easy. So take f of, I don't know, 10. We'll calculate that. Let's calculate f of square root of 7. And let's take f of -2. Try to calculate that on your own by plugging it into your calculator. Just practice plugging it into your calculator, essentially. So in this case, we're going to take 750 times 1.37 to the 10th power. Now, make sure you don't multiply this first, these two numbers first, because order of operation says you have to do the exponent first onto this number before you multiply it by the 750. If you just type it in like this on your calculator, it's going to know to do the exponent first. So we get, I forgot, 17 468.96 rounded to 2 decimal places. $750 times 1.37 to the square root of 7 power. When I typed that in, I got 1725.00. That's rounded to 2 decimal places. It does go on further. And when I plugged in a -2, I got approximately 399.60. All right. Any questions about that? Does that make sense? Okay. Let's do one more of those. Let's do this one with E. So let's take 1,600 E to the 0.12x. And I want you to find the function when you plug in 11, and then what's the output of the function if you plug in 22? The one thing you need to do when you're doing these types of things, when you have multiplication in the exponent, is make sure that when you plug it in, your calculator knows to do the multiplication before it takes the exponent. So what you don't want your calculator to do is to do e to the 0.12 and then multiply it by 11. All right? So that means if I have math print on my calculator, so everything comes up in the exponents when I type it in. But if you have the classical print on your calculator, then you have to put parentheses around the multiplication here. Does that make sense? So you have to do e caret and then 0.12 times 11 if you have the classical print. Mine has math print on the calculator. You guys know what I mean by that? So, looks a little bit more like this. So, anyways, once we have this, we can plug it in, calculate. I got 5989.47. Plug that one in. I got 22,421.13. Is that right? Okay. All right. Now, before I move on to the next section, I want to take a step back and talk about just the graphs of these exponential functions. All right. So we're still wanting to use other exponential functions. So let's do the graphs of exponential functions. And what I'm going to do is I'm going to think about shifts and translations from our base or our basic exponential function. So in terms of translations basic exponential. So let's start with our basic exponential function. Let's take f of x equals, I don't know, 1.5 to the x power. All right. Now we know, since our base is above 1, that the graph is going to have this general shape. So since the base is above 1, as I take higher and higher and higher exponents, it's going to get bigger. We know it goes through the point 0, 1. Any other points we know it goes through? What happens if you plug in an x value of 1? What do you get out? What's that?
Flat line.
I get
a flat line.
No, I'm sorry, the x of 1, not base of 1, x of 1. So if I plug in x of 1 on this particular function, what am I going to get out?
1.5.
1.5, right? Yeah, no tricks there. I'm just saying, notice that if you plug in 1, you get your base. I didn't write this down the first time, but all exponential functions do that. When you plug in 1, you get back the b, whatever the base is. So that's another point on this graph as well. And in fact, if you're given a graph, how would you figure out what the base is? You just look at what point it goes through when the x value is 1. If the point is 1, comma 1.5, I know the base has to be 1.5. If it's 1, comma 3.8, I know the base is 3.8. If it's 1, comma 0.7, I know the base is 0.7. So that's my basic exponential function. And if I ever want to figure out, or if I'm ever given a graph of an exponential function, and I want to figure out, well, what's the base if it's a basic exponential function? I just say, well, what point does it go through when the x value is 1? What's the corresponding y value? Now, let's think of shifts of this basic exponential function. If I want to move the exponential function up or down, remember back when we were translating, we added a k when we moved up or down? Well, that's the same thing. So vertical shift would be a new function taking 1.5 to the x power, and then I'm going to add k at the very end. If I wanted to horizontally shift by, let's call it h, because that's what our usual horizontal shift variable is. Well, remember what we're going to do. I'll use G again, I'll reuse that. Is we take our x and we replace it with an x minus h. So notice that the minus h would be inside the exponent. So that's what I'm getting at. The horizontal shift happens inside this exponent. The vertical shift happens outside after the whole function. And if I wanted to flip around the x-axis, a flip around the x-axis would make all my outputs negative. So a flip around the x-axis, I would negate the output like that. If I wanted to flip around the y-axis, what I would do is not negate the output, but I negate the input. And the input is that x on my exponent. So when you flip around the y-axis, the negative goes into the exponent. And by the way, this is what I was saying earlier. my rules of exponents are such that this is the same thing as 1 over 1.5 to the x power, right? Negative exponent is the same thing as the reciprocal taken to the positive exponent. Okay. So my shifts of this basic function are just that. Those, oh, and we didn't vertically stretch and horizontally stretch. Horizontally stretch, we're going to multiply the x by a number. Vertically stretch, we're going to multiply the outside by a number. Okay. I'll do that in this, I'll write that over here. So vertical stretch, slash shrink is doing this. And then horizontal stretch or shrink, depending on what the A is. That happens in the exponent. So whenever we're adjusting the inputs, we're adjusting the exponent. Whenever we're adjusting the outputs, we're adjusting after we've calculated. That makes sense? Either I multiply if I'm stretching, or I'm adding, shifting it left or right, or I'm flipping it, negate the whole thing. That makes sense? So we're going to see a lot of those types of functions, in other words. All right, we're going to see a lot of those types of functions. Where it's going to be a base exponential function, and then we have some other stuff tacked on to it. Okay. So that's why I bring that up. Now, 4-1, the end of 4-1 and the beginning of 4-2 are basically the same thing. So I'm just going to call this all 4-2, all right? But note that it does, the end of this comes in 4-1. So the end of 4-1 is the same as the beginning of 4-2. So 4-2 is called exponential models. So these are mathematical models that we can use to solve problems. So the first ones that they start with, and this actually happens in the end of 4-1. So I'm gonna, again, all of these are exponential models, but they use a couple of exponential models in 4-1, and then they use more exponential models in 4-2. So I'm doing it all under the guise of 4-2. So the first exponential models we're going to look at are compounding interest. So compounding interest. M times per year. The model is the following. A equals P 1 plus R over M to the MT. Now in other classes, you may see slightly different letters. Some people will use just P for here and P0 for here. Some people will use a K instead of an R. Some people might use an X instead of a T, right? But it's the same model. Whatever letters you choose. These are the most common letters that we usually see on this. So I'm trying to use the most common ones. And these are the ones the book uses too. But there are other scenarios in which they use other letters. So what does A stand for? A stands for the amount. P stands for principal, which is just your initial amount. R stands for the rate. M stands for the number of times per year. That interest is compounded. And T stands for the time, usually that's in years. Normal. Now this is, in actuality, the formula in which all of our banking relies on, right? This is the formula, and then other derivations that are based off that formula of all of the banking stuff that we deal with on a day-to-day basis. So if I go and I put my money into a bank and it gains 2% interest monthly, that's the formula we're going to use. If I go and get a house loan and I wonder, what my payments are going to be, that formula comes into play, right? It's not just plugging things into that formula, but it's a little bit more complex in that situation. But that's the idea. Compounding interest M times per year. Now, I want you to notice something about this. We have inside here, let's say I let the R be 1 and the M be 1. Or not the M, excuse me, the T be 1. Notice I had this kind of a structure inside of that formula. So if you compound more and more and more often, until you get to continuous compounding, this piece of the formula is going to change to an E. Remember, E was the limit of this as M goes to infinity. I used N in mine. No, we're using M. So it turns out if I'm compounding interest, not just M times per year, but continually. So I let M just get bigger and bigger and bigger and bigger. Then that formula turns into this one. A equals, we still got the P. This whole thing changes to E to the R times T. So the R and the T both basically end up in the exponent. I know that's weird, but that's how it works with limits. E is our 2.71828 irrational number that we looked at earlier. And then the A, the P, the R, and the T are exactly what the A, P, R, and T are over here. So if we're talking about continual growth or continually compounding interest, we use this. If we talk about compounding interest in times per year, we use this. These are going to be the two exponential models we're going to use most often. And we'll see that not only do these models apply to monetary problems, but they can also apply to other types of situations as well. Does that make sense? So those two formulas. So make sure you have those two written down somewhere and you know what the numbers are. Now, what makes these exponential models is that oftentimes the T is going to be my variable. Oftentimes I'm going to have a variable of T. And because the variable of T is in the exponent, that makes it exponential. So let's do an example. Let's say we put $5,600 into a bank account, earning 4.25% interest, compounded monthly. Let's first write an equation for the amount of money in the account after time t. So what this means is we're going to create our equation. Now we know it's compounded monthly, not continuously. So just once a month. So I know it's going to be utilizing that formula. N equals P times 1 plus R over M to the MT. What pieces am I given? Well, if I'm putting $5,600 into it, that's my principal, that's my starting amount, the amount I initially put into it. I know my P is 5,600. 1 plus my R is going to be my interest rate, but I have to write it as a decimal and not a percent. So be careful about that. So in this case, my R has to be written as 0.0425. If I put in 4.25, not gonna work. So R is our rate, which is our percentage of interest written as a decimal. And then my M, well, since we're dealing with this monthly, M has to be 12 because there's 12 months in the year. Now, both this M in the denominator is going to be 12, and also this M in the exponent is going to be 12 too. So the M in the denominator and the M in the exponent are both 12. And then the natural ask is, how much is going to be in my account after a certain amount of time? Let's say we can leave it how much in the account after, let's say, 10 years. And then let's ask how much is in the account after 20 years. Well, this is just like plugging in values into an exponential function, just like what we just did, right? We're plugging in values into an exponential function. This is simply an exponential function with this ugly base, right? This is just a number in the parentheses. It's an ugly base, but it's a base. So I just plug in the 10 and plug in the 20. So the amount that I have after 10 years is going to be $8,559.28. Anybody else get that? The amount we're going to have after 20 years, well, I just plug in a 20 for my T. And I get $13,082.36. Any questions about this? Yeah, this is just essentially the same thing as plugging in into an exponential function, although again, this number is kind of a ugly looking number for our base, but it's perfectly legit number, right? Some number in there. The compounding periods that we're gonna most often see are probably like monthly compounding. But you may also see quarterly compounding. Quarterly means 4. And if you see semi-annually or biannually, that means 2, twice a year. And if you see yearly, that's just 1 time a year. I would say yearly, quarterly, and monthly are the 3 most common ones you'll see. Yearly, quarterly, and monthly. But you could do any m times per year. If you wanted to do 70 times a year, just use m to 70. That's never going to happen in a banking situation. They just don't do that. They either use daily or monthly or yearly or quarterly or those types of things, but it is what it is. So let's do another example. All right, I want you to do this. I'm just going to change the numbers here. And then I'll change the time periods as well. So let's put $8,000 into a bank account earning 7.5% interest compounded quarterly. Let's write an equation and then ask how much is going to be in the account after, I'll do 20 years and 30 years. Try this one on your own. All right, so we're putting in $8,000. It's earning 7.5% interest compounded quarterly. That means my R is going to be 0.075 and my M is going to be 4. So my general equation that I'm going to be using is this one. How much is in the account after 20 years? I'm going to plug in a 20 and for the T. And after 20 years, I end up with $35,358.98. Again, that's just rounded to 2 decimal places. After 30 years, means I plug in a 30 in for my T. By the way, if you have to do this multiple times, hopefully you know this, but if you just hit second enter on your calculator, then you can just go back and change the 20 you just typed in to a 30. You don't have to type in the entire thing over and over and over again. We get 74,336.93. By the way, if you notice, you went from 8,000 to 35,000 in those first 10 years. In the next 10 years, you gained almost 40,000, about 39,000. So your amount of gain in the last 10 years was more than you initially had after 20. So you more than doubled in those last 10 years. Okay. This is how interest works. Anytime you're growing, we get this nice shape. Remember, the exponential function has this nice shape. Now, it might be shifted, might be stretched, whatever it is. But as I move to the right, it starts shooting up pretty quickly. And in fact, this type of growth is actually faster than any type of polynomial growth over the long run, right? Maybe not initially, but over the long run, this is faster than any type of polynomial growth. So this is faster than growth than like a parabola is as you move to the right. Again, as you move far enough to the right, eventually this exponential will overtake the parabola. All right, any questions about compounding m times per year? Pretty straightforward. Well, let's do this. Let's say we put 104,000. Be nice to have 104,000 put in a bank account. Earning 4.0% interest compounded continually. I want you to write an equation for this. And then let's do the same thing, but we'll say how much is in the account after 15 years, and then how much is in the account after 30 years. Try this one on your own, too. All right, so if we're compounding continuously, this is the one where I have to use E. A equals P times E to the RT power. And all of the same things apply. My P is the initial amount. In this case, it's 104,000. My R is an interest rate of 4%. That's 0.04 for the R. And then E is just E, right? E is just the number E. So the amount of money in the account after 15 years can be calculated by taking 104,000 times E to the 0.04 times 15. I have not calculated this yet on my calculator, but it goes pretty quickly. All right, I get an amount in the account after 15 years of $189,500.36. After 30 years, well, I just replaced the T with a 30. Instead of a 15. And after 30 years, you have 345,292.16. All right. Again, this is how compounding interest and growth works, if it's exponential. Might start off fairly steady, and then all of a sudden it just shoots up, right? Start out with 104, after 15 years, you earn an extra 85, and then the next 15 years, you're out earning 160,000, whatever difference is there. 155, 160,000, something like that. Any questions about this so far? The bank interest stuff? Good? Okay. I think one example of continuously compounded interest in a bank is good because a lot of the other models that we're going to see in here are also going to be continually compounded interest models, just not interest in a bank account. So let me give you an example. Let's say a population of a city is currently let's use 104,000. Okay. And it's projected to grow at, I don't want to use 4% again, I'll use a different percent. Let's say it's projected to grow at 2.3% compounded continuously. For the next 30 years. Let's write an equation for this scenario. Well, what do you think we're going to do? Well, compounded continuously is still A equals P e to the RT. Now, just be careful. A lot of times when you get into non-monetary, they'll switch up the letters on you by a little bit. Okay? So when you get into something that's not financial related, instead of using P, what a lot of times they'll do is use A sub 0, or they'll use K instead of R. I think our homework uses R and A sub 0. Because we're no longer in the financial scenario, it's not a principal anymore, it's just an initial amount. And that's what A sub 0 stands for, the amount at time 0, the initial amount. So they don't use that. And then some books will use K instead of R for the rate. Our book uses R, we use R mostly. But you'll notice that it's the exact same idea. In fact, I even used 104,000 on purpose. Probably could have used 4%, but I didn't. It's the same idea, right? my amount is equal to 104,000 e to the 0.023 times t. And then if we say, what will the population be? In 10 years? The same problem as we just did, right? Other than now we're dealing with people instead of money. Plug in a 10 for t. I haven't done this yet. I got 130, 894.40. Now this is in people, so it might ask you, instead of round to 2 decimal places, because there's no 0.40 of a person, it might ask you to round to the nearest whole number if we're talking about people, right? Instead of rounding to the nearest cent, round to the nearest person. Let's do another one. Example. And we'll do the city population again. Let's say the population of a city is currently 35,800 people. This time, let's assume this city is getting smaller. So the population is projected to decrease continuously at a rate of 1.2% for the foreseeable future. So the key here is we're going to decrease continuously. If we decrease continuously, am I still using, whether it's this version or this version? Am I still going to use that same equation?
Would you just make the rate a negative number?
Exactly. That's exactly the conclusion. Anytime we're decreasing in a rate of something, yes, we still use the same equation, but our rate now just becomes negative. So a decrease is a negative rate. So everything's the same. Except we're gonna use negative 0.012 as my rate. And that could happen with monetary problems as well, right? You could invest in a stock and it could lose money for you over a certain point, a certain amount of time. So anytime we're decreasing, use a negative rate. Just use a negative R value. Increasing, we use positive R values. Let's ask, what will the population be in 6 years? Well, in 6 years, we can figure that out by plugging in 6. I got 33,313.01 or 33,313 people. If I round it to the nearest whole number. Some questions may, just read the question, some may be okay with rounding to 2, some may ask for the whole number. There it is. Any questions about that? Now, I want you to notice that in all of the questions we had from our equation, so all of the questions we had that originally came from our equation, we ask how much is going to be in the account after a certain amount of time. Or how much is something going to be worth after a certain amount of time? Or how many people are there going to be after a certain amount of time? And we gave you the time. We want to eventually be able to say, well, I want to know how long it's going to take until this city is size 28,000. Or how long is it going to take for my bank account to reach $100,000? In other words, we're going to be given an amount and asks, well, how long is that going to take to happen? Let's find the T that gives that amount. And that's really what the next couple of sections are all about. In order to solve problems like that, we're going to have to be able to use logarithms, all right? And the next few sections, 4.3, 4.4, and 4.5 are all about logarithms. And then 4.6 and 4.7 are all about solving exponential equations, right? Like what I was just talking about here. Everybody okay with that? So that's why 4.3, 4, 4, 4, 5 are all about logarithms. By the way, there are other exponential models that I did not go over yet, that I'm kind of skipping over right now. On the homework, I was making sure on the homework, but on the homework, the only two models you'll deal with are compounding m times per year and then compounding continuously. Right, those two examples. There's also some half-life models and some doubling time models, that kind of thing. And we might see those a little bit later, but not this class period. Okay. So what I like to do then is start, we won't get too far into this, but we're going to start in 4, 3 and 4, 4. We're going to do these kind of simultaneously. A lot of times when we introduce a new topic, the first section is called such and such functions, and the next section is called the graphs of such and such functions. This is one instance of that. So this is logarithmic functions. That's what 4, 3 is about, and 4, 4 is their graphs. Since they're connected, I'm going to do them the same time. We're going to kind of go back and forth. So we're going to look at logarithms, or shorthand, we call them just logs. Okay. So a logarithm is a special type of math function log subscript b of m is equal to y means b to this power of y to the power of y is equal to m. Okay. That subscript of b is the base of the logarithm, which is also the base of the corresponding exponential piece, right? Which is base. So b is the base of the logarithm. And just like before, because it's connected to base of an exponent to a power, we force our base to be positive and not 1, just like the exponent. All right. Now, let's do some basic computing. And we're gonna solve for a variable. Let's say I have log base 4 of, we'll use x as my variable, is equal to 5. So if I have this scenario where I know the base, and I think of this as being the input into the logarithm, and the output being the 5. So if we think about it that way, I know the base and the output of the logarithm. How would I solve for x? Well, the easy way to solve for x is just to say x is equal to 4 to the 5th power because of the meaning over there. So x would have to be the number 1024. If we said log base 2 of, I'll call this one z, is equal to 3.75. Same thing. In order to solve, I do a rewrite and I say that means z is equal to 2 to the 3.75 power. And then I can just type that in my calculator. I get roughly 13.45. Later on, we'll see how to check our answers on that. But we'll trust the process. Okay. Now here, both of these examples, it was fairly straightforward because the variable was inside the argument for log. Inside the argument means the m part here. Okay? You can, in certain other instances, have a variable in your base or your variable in your output. Like, if we said, we're still solving for the variable. Let's say we had log base 2 of 32 is equal to y. And we need to figure out what y is equal to. By the way, I'm going to show you this way right now. There's another way to do this as well. We'll see that later. So we know that 2 to the power y is equal to 32, or you could have written 32 is equal to 2 to the power y. What do we know about 32? What is 32 written as 2 to a power? It turns out 32 is actually 2 to the 5th power. And if 2 to the y is equal to 2 to the 5th, we know that y has to be 5. Okay? That is one of the things about exponents that is intuitive and true, is that if you have the same base raised to a power equal to the same base raised to another power, the powers have to be equal. How about this one? Let's take log base 3 of 81 is equal to n by n. And then I want you to do this one. Let's do log base 3 of 1/9 is equal to, we'll do w for our variable. I want you to try to solve those two using the same technique I used over here. So we're asking ourselves, what power do I raise? What power when I take 3 to the nth power gives me 81? Well, 81 is 3 to the 4th power. Therefore, n has to be equal to 4. By the way, 1/9, what power do I raise 3 to get 1/9? That one. Well, what about 9? What do I need to raise 3 to get a 9? 9 is 3 to what power?
2.
2, right?
So would it be
-2, right, exactly. So this is 3 to the -2 power. That a negative exponent means reciprocal thing again. Okay? So 1/9 is actually 3 to the -2 power. And once you do that, then it's obvious that my variable w has to be -2. Now, you can also solve for the base if you're fairly clever and you understand what's going on. Let's say I have log base B of 128 is equal to 7. I'm asking what thing raised to the 7th power is equal to 128. I believe 128 is 2 to the 7th power, right? And the same thing holds true on the equality, like we were doing over here. If I have base to a power equals base to a power, and the bases are equal, then the exponents have to be equal. Well, over here, if the exponents are equal, and it's base to an exponent equals base to the same exponent, then the bases also have to be equal, all right? There is a caveat there. Remember, we assumed that my base was bigger than 0 all the time, right? So as long as we're forcing our base to be above 0, I can assume that these Here's an even trickier one. Let's take 49 to the 3rd power. Apply log base B to 49 to the 3rd power and set that equal to 6. This means B to the 6th power is 49 to the 3rd power. Now I want a 6 as my exponent over here on the right, not a 3. So what I'm going to do in order to accomplish that is I'm going to rewrite 49 as 7 squared. My rules of exponents would say the right-hand side can be rewritten as 7 to the 6th power. This is the power to a power rule of exponents. Again, since the exponents are equal, that's going to force my bases to be equal. Again, remember, I always assumed that the base was above 0, okay? If we actually solve this equation, if you put a b in of -7, it would have also been true, but we assume our base has to be bigger than 0, real number bigger than 0, not equal to 1. Okay with that? So we just have one answer here because of the nature of how logarithms work.
Just want to ask, for that power to power rule, is that just multiplying the 2 times 3?
Yeah, multiplying the exponents, so power to power rule, multiplying the exponents. Yeah. Now, having to rewrite everything in terms of an exponential function and then working through it kind of gets old pretty quickly. All right. It's not terrible in certain situations, but it does get old. And so what we're going to look at is some logarithms that I can calculate with my calculator. All right. The 2 logarithms that are on my calculator, that are featured on my calculator, is a logarithm with base 10 and a logarithm with base e. All right. Log base 10 normally we write it as just log with a 10 as our subscript and then whatever. On the calculator, this is just my log without a subscript. All right, log without a subscript means log base 10. So this is on the calculator as a button on our calculator. All right. The other log that's on our calculator is log base e. Log base e on our calculator is actually ln of x. Log base e is also known as the natural log because of the connection between continual growth and e, right? So that continual growth is a growth that happens a lot in nature. And so that's where the name comes from, natural log. It's the log that you see in nature, right? So natural log. And that's why it's an ln. ln stands for natural log. You might say, why didn't you use NL? Well, that's because it was originated not in English. So log natural is, you know, the way most, I forget if this was, can't remember where it originated, but in Europe. And so the way that many of the languages are written, in English, we use the word natural first. In Spanish, you switch it. In Italian, you switch it. Most of the languages, you would. So anyways, That's it, natural log, and this is, again, ln means log of base E. And this is also on the calculator. And I can simply utilize the calculator if I need to calculate something with natural log. Okay. Now, obviously, what we were just doing in certain instances, you'd still convert into an exponential. So for instance, if I wanted to solve for the variable and I say, well, natural log of x is equal to 3.9. What I'd probably do is still convert and say that means e to the 3.9 is equal to x, or x is equal to e to the 3.9, and then just calculate this. And we get an x value of about 49.40. Okay. But here's where it comes in handy. If I say natural log of 38 is equal to y, if I were to have tried to rewrite this as an exponential equation, I would have had e to what power is equal to 38. And you'd say, e is an irrational number. I don't know what power to raise and get me 38. Right? I don't know what power to raise to get it to 38. So that's not going to work. Or if we said, let's take log base 10 of 917, you'd say 10 to what power is 917? I don't know, right? So we wouldn't be able to do that. These two problems, using the methods we were just dealing with, okay? Because 38 is not a nice power of E, and 917 is not a nice power of 10. But with our calculator, we can just type in natural log of 38 and get about 3.64. Everybody okay with just typing in natural log of 38? Hit the ln button on your calculator right next to the 4, and then input 38. And the same thing over here. If I go log base 10, or just log on my calculator, of 917, I can get a z of about 2.96. So I'm just plugging this into the calculator. And getting a value. And so a lot of times we think about these logs as being connected to exponential functions, and they are. But also we can think of logs as being their own functions, their own inputs and their own outputs. Just like these two, we're inputting a 38 into the natural log and getting out a 3.64. We're inputting a 917 into the log base 10 and getting out a 2.96. All right. Well, I'm gonna stop there and we'll keep moving on into more of 4.3 and 4.4 next time, okay? And we'll see a lot more properties of logarithms next time. All right, other than that, there's some homeworks due. I forget which homeworks are due. 3.7, 3.8, no 3.8, 3.9, and then 4.1, 4.2 are also due this Friday. Okay, the 4.3, 4.4, we're obviously not done with. That won't be due till next week. Okay. So there's gonna be 3 homeworks due this week. The 3.7, the 3.9, and then the 4.1, 4.2. All right, other than that, I will see you next week.